Okay, welcome everyone to today's NORA Friday afternoon webinar. The sun is shining and it's a perfect day for a good talk. My name is Klaus Pettersen and I am the CEO of NORA, and it's my pleasure to introduce Nabil Belbachir today. He's a research director at NORA and the head of Smart Instrumentation and Industrial Testing Unit. Nabil is a specialist in artificial vision, bio-inspired event-driven vision, 3D vision, and smart cameras, with a special focus on system and method design. And I'm really looking forward to your talk today, Nabil. My background is within computational neuroscience, so I really like bio-inspired artificial intelligence. Today's talk will last about 40 to 45 minutes. Then we will open up for questions. Most of you know the rules, so please use this Q&A button at the bottom of your screen for questions, and I will read them up one by one after the talk. The title of Nabil's talk today is Bio-Inspired Vision, taking smart cameras to the next level. Nabil, the screen is yours.
Thanks a lot, Klaus. Thank you very much. Thank you for the invitation, and thanks that I can share some of my research work with you and with the people here. So I'm very happy to do this. And hello, everyone. So as Klaus said, so I am research director at NORA, and I worked in the past 15 years on bio-inspired vision, how to get inspired from the biology to develop vision systems. And I'm really happy to share this with you, and to save time, I will just start now, and I hope you will enjoy the talk. So the first thing is, what I want to speak about is why actually we are bothering with the bio-inspired vision, or biology, basically. So the main thing is that biology is our master teacher. So engineers or computer scientists or computer engineer, when they would like to develop things, they look basically into the biology, because we consider biology as the best machine. And there are a lot of turning points in the history of science, how people using biology for developing things. And one of those is Sigmund Freud, basically, who is the neurologist and founder of psychoanalysis. He had a huge impact and effect for the creation or the coining of the term artificial intelligence in 1955 in USA. So basically, a lot of people who were influenced by the work of Sigmund Freud, because he was one of the people who did a lot of experiment on biology and try to understand biology, and a lot of his disciples went further his way, and they find that creating a new discipline, artificial intelligence, was a word at that time. And the work for sure started in Europe, but because of the Second World War, a lot of people moved to USA, and that's why it was created in US. But there was also some experiment trying to challenge biology and understand how it works, and try to duplicate it for systems. And one of those was an experiment that I will show now in 1951 on human vision perception. And this is Professor Theodor Erisman in the Innsbruck University in Austria, 1951. And he wanted to understand a bit how the human perception works. And so what he did, he has a student called Ivo Kohler, and he was wearing a glass that can sweep, I would say, you see everything upside down. So, and this, I will show you a video here that will explain a bit how this works. So he was wearing this glass for about 10 days and try to understand how the human brain or the human vision will adapt to the situation. And what he did, he just wear this glass for 10 days and then live with it. And then we are looking now at the video here, how it works. And it was about, first, what you see here is the Professor Erisman giving the glass to his student Ivo Kohler. So, and that's for sure the first impression how the life looks like. And And then it was 3 phase how the human vision adapt to the situation. So the first 3 days was the very difficult days, because the brain has to basically flip the whole scene upside down to give information to the motoric control. And you will see now, yes, what is going. Yeah, so let's see. I will just show 5 minutes of the video, and then I can discuss about it. So yes, the first, I'll say the first phase was the first 3 days, where what is the completely new situation for the brain, and the person, I would say all motoric control changed. So he will be confronted 3 days to new situations, because the whole the eye are sending visual scenes which is turned to 180 degrees, and you need to adapt the whole activities afterwards. So let's see. And yeah, you see that everything is flipped in the other way. When he turn his head to the left or to the right, then he is looking, I would say, in the different position than what is expected to be when you have we don't have the glass. So he needed a lot of help to work out, as everything is upside down. Yes. So, and that this is a true story basically. So it is not the movie was made very nice, but it's true story. He was living really with 10 days with this glass. And he's showing some specific situation where, like here, you have a bar at the entrance, which is on the top side, but he see this as it is on the yeah, below. So he's yeah, that's and then he did some exercise here, so you can, yeah, it's a lot of fun here, but it's really it's a mixture between fun and understanding how this really works into the brain. So it's yes, so it's stuck. Yes. Then we'll see with this. Yeah, it's oops. So that's, yes. So then that was the first part. Then let's go to the second stage, which is between 3 and 5. And it's amazing that after 4 days, it start to adapt basically, and he could be much more flexible when he's moving. He doesn't have the full capability as without the glass, but starting, actually, it's amazing how the human can adapt to the new situation. And yes, then he was ready to enter, yeah, to do the same path. So, and then do some exercise in a good way. Yes, that was yes, after the second. And then basically many things were said how this happened, that the human brain could really adapt to this new situation. And it was because we have references. The human put some references, and the body of the person itself is one of the reference that help that you can adapt very, very fast. So, and then the first 5 days was or 4 days, it was perfectly moving, as everything was fine. And then after 10 days, when he removed the glass, basically everything went back again. So he needed also some 4 to 5 days adaptation to get back to normality. But that's one of the experiments that showed that how the human perception works, and how the biology is amazing in adapting to a new situation. But that's one turning point. But is it the first one? I would say no, it's not the first one, because like 1,000 years ago, there was also some experiment with the human vision. And I would say, if you know the book of optics of Al-Hasan ibn Haytham, that's which was invented in 11th century, where he described basically a full visual system, how it works based on experiment in human, what is called also camera obscura. So he even realized the first camera at this time. And the most important, basically, argument that he got was that the vision occur in the brain and not in the eye. So we don't see with our eyes. We basically, more than 90% or even more, of the whole vision occur in the brain. And that is very, very important. That's what brings that many people try to understand what is the brain and how the vision works. And if we look at the brain, so we know that we have more than 80 billion of neurons, and that's the vision has about 30% of the neurons is using 30% of the neurons is used for vision. And then you have also, if you look at human vision, you have two parts. You have the eye, where we have the retina, which is the most important as a sensor modem. And then you have the optical nerve and some optical communication to go to the visual cortex, or primary visual cortex, which do most of the processing. And if you go into more details to look into the brain, how the vision in the brain looks like. So you have in the visual cortex, or the visual part of the brain, a lot of V's, V1, V2 until V7, and then more of those. And every part of the brain is responsible for something. So the first one is the motion, the V2 is stereo vision, then you have the color, then the texture, then you have part of segmentation grouping. Some areas is responsible for recognition, others for attention, others for memory, and then you have some for decision making and sensor motoric integration, and so on and so forth. But I would say that is basically a categorization of the brain, but not everything is 100% clear and known, but it's a lot of assumption as well. There are many things known in V1, V2, but the rest is more a lot of about experiment and assumptions that are made by neuroscientists and biologists. Then we go to the other part, which is the retina, which is the human detector. So the retina is this yellow part on the back of our eye, which is light goes through the cornea and through the lens into the retina, where we have a lot of photoreceptors converting the light into electrochemical signals. So our neural computation is not just electrical signals, but you have also chemical activities as well. And the retina has 5 important tasks, like, as I said, changing transduction, wavelet encoding, and then dynamic range adaptation, and chromatic adaptation, spatial filtering, and the most important is data compression. So that is very important to know, that the human vision or biological vision doesn't work like the standard cameras. So it's asynchronous, it's not synchronous. There is no frames. It's what they call in the biology is spikes. So every the human eye, at least, and some animals' eyes are sensitive to light illumination change, and that means that they don't send data to the brain for every signal, but only for changes within specific threshold that is adaptive at the human, and they call them spikes. And that's why you have huge compression at the retina and sending signals to the brain. And just going very short into details about how the retina works here. So on the right side, you will see that we have on the bottom of the figure, you see how the light is coming from the bottom all the way to the top. And on the top, you have the photoreceptors. You have 2 types of photoreceptors, the cones and the rods, which have responsibility. One is for the daylight vision and color vision, and the others is more for the night vision and achromatic imaging. And we have, I would say, 100 million cells, 120 million cells for rods, and 6 million for cones. And those light signals, which are transferred into electrical signals, they go into what so-called ganglion cells, which is on the bottom here. And the ganglion cells, you have 2 types. You have off-center and on-center. And this ganglion cells has a pre-processing inside, which look at the spatial contrast, and they only send spikes or firing when you have contrast change, basically. So when the center, this contrast between the center and the neighborhood is changing, basically. So if you are in an area where you don't have any change in the scene, basically the brain doesn't get much spikes or much information because there is no change. But when you have a lot of change, you have a lot of information going to the brain. And that's very good for not using so much power of the brain. Yeah, so it's and that's what is basically is a, I would say that's it's very old representation how a neural image looks like coming from the ganglion cell. So you get a compressed spatial contrast from the ganglion going to the brain that will do the rest of the processing. Now, why we say bio-inspired vision? It means that what we would like to mimic the biological visual intelligence, and it's partly the retina, but mostly the brain in the vision. And the main issue is that we don't know much or everything about the brain. We know a few things, but not everything. And but the most amazing thing about the brain is that it has a huge amount, like more than 80 billion of neurons, and every neuron is a kind of own computer, so completely parallel processing. You have 80 billion processor like in the real world in parallel that they can process data, and they have what they call synapses, which is neuronal communication between neuron, and they have some memory formation also functions. It means that you have 80 billion multiplied by 1,000 synapses, so you have a huge amount of communication. And then and all this is in a very small object and very low weight, so 1.4 kilo, and basically the average power consumption is about 20 watt, which is basically 20% of the whole unit. And if you look at the best computer that you have now, or the one of the best, like Summit, which is for 4,600 nodes with 1.6 terabytes, it costs $110 million, and it's 15 megawatt, which is like 1 million more than what the brain consume, and it's a huge room with a lot of computing, and that is basically a kind of fraction of processing and capability that the brain has. So you have these huge machines now, but still it's really a huge task to try to duplicate the brain, not just in size but also in performance and capacity. Yeah. So that was basically the introduction to just to give you some insight about biology and what is some terminology and what is ongoing here, and motivation. And then I will give you some different perspective about bio-inspired vision. So there are a lot of areas which working or were designed for bio-inspired vision. One is in the electronic side, what they call neuromorphic engineering. And that was initiated by this person called Carver Mead in the late 80s, where he tried to build electronic system or VLSI systems to mimic neural computation. You have another area which is called computational neuroscience, and there is a huge amount of people who worked on this. But one of the people that I like, and I was a bit influenced in my work, is David Marr, who was one of the pioneers of building this bio-inspired visual perception system. And then there is also another area on bio-inspired vision where people try to look at optics, bio-inspired optics, like the eagle who can see object at 2 kilometers and at the same time object at I would say 1 meter. So he's has a fantastic I would say vision for having different lenses on his eye, and there is few people working on this what he called the foveated imaging with bio-inspired optics. And then you have also the other community which working looking at or who invented basically the deep neural networks, and they use the visual primary cortex of cats to try to build the first network. It was Hubel and Wiesel in 1962, basically, who are two physiologists and doctors that did a lot of experiment with the cat. And Fukushima, Kunihiko, he was one of the first person who implemented this as deep neural network in the 70s and 80s. And what I will present now in the second part of my talk about my research work is basically some areas which mixing between neuromorphic engineering, computational neuroscience, and the deep neural network concept here. So that's what we call bio-inspired vision, and it's event-driven sensing principle. So what I was involved in the past basically is to try to duplicate the vision of the bee. What is different in the bee, that the bee is not sensitive to spatial contrast like the humans, but it's more to the temporal contact. That's why the bee can see very, very fast moving objects while they don't have very good spatial resolution. But the human cannot see very, very fast. Like he doesn't have a very high speed vision like the bee, but he has a very good spatial resolution. And as I said, it's the same concept with, I said, cones and rods and the ganglion cells, but in this case that the ganglion cells doesn't spike for spatial contrast change, but for temporal or relative temporal contrast change. And this is the one in violet here, or lila, is the ganglion cells which send this this temporal contrast change. And there was there are a lot of electronic circuits who mimic basically the ganglion cells and retina. And one of the coolest one is one done by Toby Delbruck. He was in Caltech in the 90s, but also in ETH Zurich afterwards in the 2000s. He was able to develop a VLSI circuit that was very compact, very small, very low power, and can be put as a pixel basically. And that's led to this chip design of making new chip that integrate a kind of photoreceptor, but also a kind of pre-processing that duplicate the ganglion cell in the biology. What is important to know about those dynamic vision sensors? So it's called dynamic vision sensors. At the end, it had different names, but they call this type of sensors dynamics because they look at the dynamics and motion detection. And they are feature-based, so they don't send frames. They only those type of cameras, they only send data when you have change, temporal change. So we call it event-driven vision sensors. And that's why they have very efficient pre-processing of visual information at the receptor, as the human does, actually. And very important is that you don't have basically a dummy pixel like a standard camera, but every pixel is very intelligent and autonomous. And it has its own circuit that can basically transfer light into spikes or events, asynchronous event, by firing when you have relative light intensity changes. And it's called temp diff pixel or transient pixel. And why bother with all this? Because having those type of sensors, so you have very three combined advantages simultaneously. One is that you have very high dynamic range because you have autonomous pixels that one can look at the bright side and the other can look at the dark side. And that's very, very important in natural environment. And then we have very high temporal resolution. So you can have 1 microsecond jitter, so like 1 million frames per second if you convert it, but it's event, so it's difficult to convert it into frames. So it's very, 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 very fast. And then you have on-chip compression, because then you don't send data, you only send data when you have changes in the scene. And what is the result of such a sensor is an asynchronous stream of events having change information, and you don't have really image data. And you will find different names in the literature, like what I wrote here, neuromorphic temporal contrast vision sensor or transient sensors. And if we just take one pixel just to illustrate how the pixel works. So you have here on this figure, you can see a graph where you have on the x-axis is the time and the y-axis is the light intensity. So what you see here, you have a low light intensity at the beginning, and then you have some changes in the relative change in the intensity. And then you see below on event and off event. With on event means that we have increase of intensity that lead to spiking to on event, and on off event you have decrease of intensity that led to spiking of event. And then you have those type of events also in the high when you have high illumination condition, like high intensity. And it doesn't matter if you have high or low. You see that you always you have this dynamic range, that you have similar number of events when you have contrast change. Looking this from visual, how this looks like. So you see here on the right side is a standard image or camera that record basically a visual scene with hand moving, and you see on the middle side this bio-inspired vision sensors, where you see event generated when you have motion. The red, we mean with the red, this what I spoke about off event, so decrease of intensity, and the blue is the on event, and the dark gray is the history. So you have the time, so you can basically a spatial temporal data generated while you have motion. For sure, one of the first things that we did, and many people did, is that it's very difficult to process this data because it's not standard for computer vision and image processing. So you get events asynchronously sent. So what we said, okay, let's start with the first thing, is to accumulate every 40 milliseconds those events and build what we call pseudo frames, and that's what you see here. So you can accumulate this and build pseudo frames to start to do standard image processing algorithm or computer vision. And in this case, we accumulate 40 milliseconds to get 25 frames per second. But that's not the main purpose. It just that was the start of the research to try to see if one can use standard algorithm for processing those data. One important thing to know is that the difference between clock-based cameras and asynchronous cameras or event-driven cameras. So in clock-based cameras, you have this graph where you have photoreceptors, and then you have light intensity, and then you have readout electronic that integrate the light over time to generate frames. So you have, I would say, 25 hertz or 30 hertz integration time, and then you are, I would say, continuously integrating to generate fixed frames independent of the scene. When you speak about asynchronous vision and transient pixel, you have basically also photoreceptors, but you don't have this integration and readout electronic, but you have in the pixel itself some circuits, and then each pixel will evaluate light intensity, and then when you have I would say contrast change, decrease or increase, then you have events that are sent to the buffer. But the new things in those type of sensor is the arbiter, which is the referee, because when you have many pixels sending at the same time events, because you have a big object, and then you have concurrent events, then you need a kind of arbiter who can structure the transfer of the event through the unique bus to the buffer, and that's what is done. And I put always below some publication that you can probably afterwards relate to if you'd like to read more about this. Yes, and then let's try to summarize this advantage of bio-inspired dynamic vision compared to standard cameras. And then we have the first one, if you have a compressed data, sparsity and parsimony. So on the right side, you have the standard cameras, and the left side, you have the event sensor. And you see that you have less data because only the event are generating data. The second, we have high temporal resolution. You see here you have motion blur on the right on the standard image, but while in the event cameras or dynamic vision sensors, you can see the edges very well. Also in dynamic range, if you lighten one part with the 1000 lux like lighter, then you can see that standard camera has issues to deal with this high or different in dynamic range, while the event sensor can deal with both, because as I said, it has this capability for wide dynamic range. Even if you change the exposure time, you still can capture both bright and dark side at the same time. And that gives us to the conclusion statement that it is physically, basically, and also from the theoretical part, it is very, very difficult for frame-based cameras, basically, to have simultaneous high temporal resolution, low data volume, and wide dynamic range, while this dynamic vision sensor have this unique property to really combine these three in one, and that's not possible with standard frame cameras yet. So let's start to see which application and which type of sensor and algorithm are used in the next slides. So let's first start with using this in high-speed vision, because we said we have very high temporal resolution, and that's how we can use this. So with high-speed vision, we mean a very fast imaging, high frame rates, and we don't mean thousands or 5,000. We mean here like 100,000 and 1 million frames per second. Basically, that's a really fast imaging. And then to process all the data in real time and to have a decision for many applications, that's almost a big issue with standard systems. And for this also you need a lot of light if you do it with standard light and a good sensitivity and resolution and so on and so forth. And that's what machine vision, high-speed machine vision use are line cameras, which have 10 kilohertz or 140 kilohertz. In this aspect, I was involved in the past in developing two types of line cameras or line sensors based on this dynamic biospar dynamic vision sensors. One in 2006, which is dual line sensors with 2 times 256 pixels, and one was with 1 time 1024 pixels. And those sensors have on-chip preprocessing, which can produce data up to 1 megahertz. It means you are really beyond the state of the art and so on and so forth. And you see here basically the camera, which is on the a rotating drum, where you have we stuck many objects on the top of it. It rotates at 20 rotations per second, so equivalent to 20 meters per second. And this is how the objects that we stuck looks like. So it's about 20 meters per second for capturing edges of the objects. And you see it's a very high speed, but it's less than 1 megabits per second for the data with a timestamp of 1 microsecond. And I will not go into the detail into the processing here, but there is a paper there and a few others as well. But the main thing is that for events, when you do high-speed event data analysis, so you are not able to, or it's not easy to use standard algorithms. So most of the algorithms for the event here are clustering to detect objects, and also categorization for detection and classification and learning methods. And I will just show examples, concrete example for application where this was relevant, and that's a real product that was generated up based on those sensors. It's Tetra Pak counting. This is a company which produced this Tetra Pak or drink cartons, which are packed into a big carton. And typically the filling machine is always filling more than 250. That's what is expected. And it was very difficult to use any system to measure it in real time at high speed. And that's why we use this type of high-speed cameras to accurately measuring the number of Tetra Pak in this machine. One of those also is in the machining industry, or the automotive industry, where you have on one side we have tanks of screws, different size, and the other side you have robots grasping the screws, and then the screws are thrown by air pressure into the area of the robot to grasp them. And then what we did is to put the camera between the tank of screw and, sorry, I don't know if you see it, but between the tank of screw and the robot to inspect for the size of the screw, the speed of the screw, the thread, and so on and so forth in real time while flying. So that's what you see here at 8 meters per second, that screws flying in front of the sensor for inspection in real time. Yeah, it's 60 kilobits generated here. And then the last one, the last selected application is for the automotive industry also. Especially when the CAN bus was invented in 1995, a lot of sensors are put in the car, and one of those was this one. It's to basically measure the drift of the cars to enable the electronics on the car to do self-calibration and automated calibration. And that's where we put the sensor below below the car, and then try to look into the floor and use the floor as a reference using optical flow and some algorithms to correct for the drift continuously of the car. Yeah. Second part, I will move to the 2D, 3D, and 4D vision using those type of sensors. With 2D, we mean images, only spatial coordinate. With 3D, we mean spatial and the depth information. And with 4D, we mean that we add the time to the depth information. And for this, I would start with the 2D. And the one of the interesting application and also product which was made in 2008 on this is traffic monitoring. So you see on the big image is the standard camera, and on the bottom left of the top left of the image, you see this event-driven 2D vision sensors, and which was used for traffic analysis. So what is used is to detect the car, because it's detect only the motion, which is very good at very high speed. So you can detect the car. We can classify the vehicles. We have 9+1 classification, so different type of vehicles for some standards. You can collect the speed of it, and we can also measure the size of the vehicle. And that is also a product which was made based on this, and it's a very small, I would say, smart cameras that's deployed in several places for traffic analysis. And just few methods here on traffic monitoring for classification, where on the daylight you use the size of the vehicle, and in the night you will use the headlight for classification, because classification is the biggest issue for traffic analysis, how to classify the car based on there is nine type of vehicles for many authorities if you would like to do traffic analysis. And yeah, that's basically during the day you are clustering the vehicle, clustering event from the vehicle to classify it, and during the night we are looking at the headlight and using the distance between the headlight to the classification. So that's yeah. The second part of this one is 3D vision, and 3D vision we mean that we are using two cameras to do stereoscopy, and that's the sensor that was here. So I will just show some, and here we show experiment with two with stereo sensors that are measuring or are capturing at the same time small moving object and high-speed object. So it's a fan that was rotating very fast together with the hand, and try to use two sensors to capture both. And one of the first method that we used in stereo vision is building kind of pseudo frames. So not matching in space-time, but building pseudo frames and then matching pseudo frames. And there is a lot of papers here that were made. It's basically, you have from the scene, you have two frames from the left and right detector, and then we can use this as a standard stereo matching with cross correlation, and then build up a kind of a depth map here. And that was working well, but we didn't really make use of the of the full capability of the sensor, which I will show why we go to 4D vision. But just to show you some examples here, but I will just go to the right object. This is like one of the main products, probably the most successful product in this type of cameras that we had, and was people counting. So you have the stereo event-driven cameras that is used to count people for security and for event management. It was used in European Football Cup in 2008, and it was used in Brazil World Cup, and it is used now in Oktoberfest and in Live Ball and many events management, because it is very competitive to the LiDAR systems, and very small, compact, low cost, and yeah, easy to manipulate. Then the third part of this 2D, 3D, 4D, we saw that for 3D vision, so we used pseudo frames, but the 4D part is basically to not use pseudo frames, but to match directly spatio-temporal data dynamically. to match in asynchronous way, because typically standard stereo cameras, you have two cameras that take images at the same time for the same object, etc., etc. But here you have events. They came when you have changes. It's sometimes that the left detector see change and the right detector doesn't see it. So you have this asynchronous type. So, and that is important to keep this asynchrony for the matching here. To do this efficient processing, because we don't create frames, we just process events. But the problem is the scientific problem. You can't match single event, big ambiguity. And it's very, in stereo vision, it's very important to have redundancy, because redundancy increases the accuracy. And it's very difficult to be very, very flexible between high speed and low speed. But what we did here, we got inspired by the work from Mar and Poggio, which is called cooperative network. It can be neural network or it can be something else, but it's called cooperative network, which use biological principle of uniqueness and continuity. And it means that the uniqueness means that we have a physical point in space that match in both the detector, and continuity that we are considering smoothness in the object that we are detecting. And we built this kind of network, a cooperative stereo algorithm network, where we map all the events coming from the pixels, and do a kind of what we call updating by accumulating event and updating the matches, and then using winner take all for this. And I just go through it here very fast. So you have the left detector and the right detector, and we built kind of a disparity network, which you call the cooperative stereo algorithm. And every incoming event will be we look for possible match in real time, and then do this continuously and updating until we find a good weight to choose the best match between the different events, and then use winner take all basically to select the high value and calculate disparity. And that's what we can see basically from this. So now we don't see the images and we don't see the depth, but we see the spatiotemporal 4D representation. So what we see is the X and Y are the image plane, and the Z is the time, and the color is the depth information. And then when the person is coming nearer, it is red, which is mean it's near, and the person is going further, so it is it's getting bluish, and that's how this 4D representation done. Yeah, and one of the, I would say, product, it's a prototype that was made, is for elderly care or fall detection. That's a Euronews documentary that was made 2012, if I'm not mistaken, on using the system for elderly home in Germany and in Finland. Yes, based on this type of sensors. But you have the link below, and you can always look at it if you are interested, because I try to keep the time faster. So the last part of the talk is using the same principle for 3D 360 panoramic vision. And basically panoramic vision use two types of camera system or vision system. One is a system that doesn't use mechanical scanning. One is called catadioptric camera, which is on the left with some mirror. Other called polydioptric cameras in the middle, and on the right. And they have issues with distortion, and especially when you're dealing with 3D. And then you have other types which have mechanical scanner, and it can be standard cameras, or it can be LiDAR that are put on the scanner and rotate, and they have issues with either vertical resolution or the price, and so on and so forth. And what we thought, as we have this unique sensor that generate event, it has a high speed and so on. Let's put two line sensor, as you see here on the right, top right, put it on a scanner and get it rotating, and then do this scanning from scanner. That's what we did basically. So you see here on the top image or the top video, a robot with this what we call a 2-core 3D. It's a 360 stereo cameras moving or rotating at 9 rotation per second. Below you see only data from one line, from one sensor, not from both, which is basically the contrast of the scene. And then we said, as we have now the contrast, why we don't try to do reverse engineering and reconstruct the image. So we have the point, and we would like to get this curve here, the light curve, and that's what we did with 3 types of filters. I just go very fast because I'm already running over time. So the first one is the contrast image, and then we did 3 filters to try to do, as I said, reverse engineering and try to reconstruct the gray level images. So on the top you have the data generated from one line while the sensor is rotating and 9 rotation per second, and the bottom is you have the gray level panoramic images. The third part is a stereo, as we have 2. So now we can do some stereo matching of panoramic views from both. But then we are getting into a very difficult scientific problem in stereo vision, which is called non-central cameras, because as both lines are rotating, so the optical axis of the camera of each line is changing all the time. So the calibration is really, really difficult, and it's a long story to speak about it in a few minutes here. So, but what we did is we applied 2 methods to calculate disparity while doing calibration in the matching itself. And one is that we use the edge image or the event map generated, and the second to use the gray level image. And this is what we get at the end. It's the 360 3D panoramic vision, where you have the color code is the red is near and blue is far, and that's on the robot moving. And then we got this this 3D 360 map, yeah, for on the stereo camera. So that was actually 45 minutes for my talk, and this is basically other activities that we're working now on bio-inspired vision at North. One is this COVID-19 for epidemiology monitoring, others for infrastructure monitoring, others for process monitoring, and others for tunnel monitoring. And if you have questions, you can just send me email and I can answer them definitely afterwards. And I put at the end here some references for further reading if people are interested to read more or to about the different topics. So you can just look at those references afterwards. Yeah. Thanks a lot for your attention, and sorry for being a bit late than expected, but I hope that you enjoyed the talk.
Yes, absolutely. At least I did, really. It was really interesting, Nabil. And I have a few questions, and to all attendees, please use this Q&A button if you have questions. So I will start because we don't have any questions yet, but these artificial neurons that you have, they're on and off cells, as you said. And of course, that means that they are very good motion detectors, as you have shown. And I was actually going to ask you about, I mean, the way nature solves this problem of motion is that you have the eye vibrating. You have, of course, a rotating part, as you showed in the panoramic view in the last part of the talk. Have you also tried out other motions with the cameras?
Yes, that's you are getting a very yeah, it's very important topic, Edward. You are speaking. You mean now about human vision, that you have this how would you call it, ego motion of the eye all the time. That is, I don't remember how many hertz you have in order to capture also some motion, and that is very. It's I would say it's a it's a background signal that the human eye is doing, that you have this ego motion. To first one is to keep the brain fed with a minimum number of signals. It's not zero when you don't have anything, so you have always something, some signals to keep it active. And the second is, as you said, to capture motion. But yes, we look into this. but we didn't really, I would say there are other people who work on the human eye, but they were more interested in the spatial capability of the human eye to have what they call silicon retina and do this foveated imaging and try to duplicate the human vision. But in our case, we thought that it is really a very big shot to duplicate the human eye. That's why we started with the bee, because the bee has a very simple biological system or retinal system. It's much less complex than the human, and the bee doesn't look, they don't have a very good spatial resolution, but they have this extremely fast motion detection. And that's why their ganglion, the ganglion of the cell is basically, they don't have this, what you call it, the off cell and the on cell. They have this for space, but it's more for time. And that's why what you say, it's very relevant on the human, but there are some colleagues which work on it, but for being very fast to have some results, I think we have selected the bee, because then it's much simpler than the human eye to duplicate.
You also talked about these cameras are very fast, as you said. What was this temporal resolution again?
It all depends on the light, but at 1000 lux it was 1 microsecond. So 1 microsecond, so it's like 1 million frames per second if you compare it to standard frame cameras.
That is very impressive. I was also thinking, now that you kind of have a copy of the retina, have you started building more complex artificial neural networks on top of that? For example, object recognition, you mentioned it, but how do you do that? How do you proceed?
Yes, it's I would say you have two parts when you do the processing. I just try to go to do. You have two parts. Just take this one. You have two parts. One part is the hardware. If you would like to duplicate the neural processings, then you need to have parallel processing units. So parallel processing units, you need FPGA, and it means that you need a lot of I would say power and a lot of nodes and huge table of a lot of processors, or you need to have ASICs. And for FPGA, that's what I can just probably I will show we had some prototype on the parallel processing FPGA for this panoramic camera. That it was limited processing, and then implemented some algorithm. And the algorithm, but that's what I was showing here. It's a very specific algorithms, because you are not looking at image and doing image segmentation and doing detection and so on, but you are getting spatio-temporal event, and you are more working on clustering event, doing some geometrical reconstruction of the event to build geometry out of the data, and then try to put this on FPGA or on DSPs and so on and so forth. But there was a long history of IBM. IBM has this very what they call it neuromorphic processor that they developed for over 40 years, and they try to build up not just FPGA but this ASICs to try to build up so many neural cells, and try to have I would say to process data from more pixels and more sensors than what we did here. Here we did it for 1024 maximum, actually. That's the maximum number of sensors that we could process in parallel.
Yeah. We have one question from an anonymous attendee. What is the effect of weather conditions on the sensor efficiency? For example, on the panoramic camera?
Yes, fantastic question. Great. So for the panoramic camera, so the weather condition is all about the housing first. So when we speak about protecting IP67 or IP65, so this housing basically was IP67. I don't know if you see it from, it's probably, I just move it. Yeah, this one. It was IP65 or IP65, I don't remember, but it was IP67. The one issue that you have with those type also of cameras is the water droplet. When you are putting, even if you have IP67, when you put those sensor in the field, then you have droplets which are stick on your lens, and then you cannot see basically. But this is one of the benefit of having this rotating, because the droplet never stand, you know, on the sensor. So and that is very good to have this rotating in this case. And with the IP67 or 65, I don't remember, then you have better protection. And then the second is when you speak about environmental condition on the weather, that the high dynamic range of the sensor helped a lot to deal with different illumination condition during different weather condition, because you can capture different you can deal with different sunny and cloudy and mixed between both, and so on and so forth. So it was it was possible, but the biggest issue is night mode, which we didn't have. So for a night mode, you need external lighting for seeing during the night. So it's not designed for the night.
Following up question on this, are any of these cases being used on offshore applications?
No, basically, let me think about it. I have to be very careful, because there is some drones now which are flying with those type of sensors and trying to do the same work for the mapping and so on and so forth. And it might be that they are also working for offshore application, but the offshore sensor are always 20 years, I would say, back. Because the certification procedure, if you would like to have a standard installation in the offshore, you need to follow up some strict regulation and EX proof and so on and so forth. So inside, no, but drone, there are some trial of this. Yeah.
Thank you. One question from Adrian Ludl. Can these sensors be used in microscopy? At how low intensity can they work?
Very good question. Yes. So the logo here is to say we work from moonlight until sunlight. So from 0.1 lux until 100,000 lux. That's the main thing. But there is like 4 or 5 type of sensors, and it depends for sure on the different which sensor it is. But it was never used for microscopy, because it was more thought for motion detection, but it was also tried for some inspection of moving objects, which is like you know, the PCB inspection and those. But it's I'm not aware it was microscopy. I don't think it's what we call microscopy. It's yeah, it's probably 10 to 100 micrometer. I don't know if this is microscopy enough or not, but the pixel size is about 10 micron. So if you use telecentric lens, it's possible to get to 10 micron basically. But we know from the Nyquist theory and so on and so forth, you need 2 to 10 times to have the right precision. So the short answer now, I would say, not that I know that it was applied, but it is possible. But I know that it is applied for also low light conditions. Yeah.
Yeah, actually, I received many questions now. The time is approaching 3, but I will take a last one. Let's see. Is the technology principle valid with night vision cameras?
Yeah, I would say in night vision it was used, but with some light. So you need some external light. And I saw for this traffic monitoring, if you saw it, it's doing traffic analysis for day and night, and this is what you get basically. So I just show it before. So it's this one, and yeah, so you can see, I think it's this one. So This is the day data, and this is the night data. So it's you can see the headlight of the car. So whenever you have light, yes, you can use it. But for complete darkness, like zero darkness, without any external lighting, no, you cannot use it.
Okay, thank you. Then I think we'll just call it a day, and thank you very much for a very interesting talk, Nabil. And this is actually our last webinar before summer, so happy summer vacation to everyone. Do as you should, write papers, do science in the summer also, and we will see you all. I think we will start up 28th of August after the summer. Thank you, Nabil.
Yeah, thanks a lot. Thank you. Thanks a lot. Yeah, thanks. Bye.